Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 3.34. The problem statement says, a rectangular block of height L and horizontal cross-sectional area A floats at the interface between two immiscible liquids, as shown below. And I've got their diagram here. Part A, derive a formula for the block density in terms of the fluid densities, rho 1, rho 2, the heights, h0, h1, and h2, and the cross-sectional area, A. It's not necessary that all of these variables appear in the final result. Okay, so let's start off with part A. We've got our diagram here. You can see the different, we have the fluid 1 density, we have fluid 2 density, so we've got fluid 2 in the bottom, and fluid 1 in the top here. And our block is right here in the middle, floating, and the block has a density right there, rho B. And then we have our 3 different heights that it mentioned right there, and then the total length of the block is L. Also not here, shown here, is the cross-sectional area of the block, which is A. Okay, and we need to calculate what the density of the block is. Okay, so we'll start off with our force balance here. We've got 3 different forces acting on the block, and I'm doing this in terms of densities and buoyancies. So we've got a buoyancy force pushing up on the block due to fluid number 1. We have a buoyancy force pushing up on the block due to fluid number 2. And then we have a surface tension force. Because the block is sitting at the interface here, there's a certain amount of surface tension that block has to break in order to penetrate that surface. Now, normally surface tension forces are pretty small, so it depends on how dense the block is, and how dense the fluids are. It may or may not be, the surface tension force may or may not be negligible in this instance. But for the sake of this problem, since we haven't looked into how to calculate surface tension forces and things like that, we're just gonna leave it out of this problem. Assume that it's negligible. Okay, then finally we have the weight force pulling the block down, its own weight due to gravity. Okay, the sum of these forces needs to equal 0 because the block is not moving. If the sum of the forces were not 0, then the block would not be at equilibrium and it would be moving in the fluid. It would either be rising up or sinking down in the fluid. But we know that it's just totally stationary. So all the forces have to be 0. Okay, now we have, we're going to add up all these forces. So we have the block 1, the buoyancy force 1, buoyancy force 2, surface tension force, and our weight, gravity force. We're going to assume that the surface tension force is 0 and that the reference frame is the interface. Okay. We've got our equation here that we've rearranged from up here, rearranged it, and we have to solve for what each one of these forces are. So let's start off with what we know. We know that force equals mass times acceleration. Okay, force equals mass times acceleration. Well, what's the mass of the fluid that has been displaced? That's going to be the buoyancy force number 1. The mass of the fluid that has been displaced is the density of the fluid times the volume of the fluid that has been displaced times gravity. Well, the volume of fluid that has been displaced is the height of the amount of the block that is in fluid number 1 times the cross-sectional area. So the area of the base times the height is the volume of the block that is displacing fluid number 1. So that is the buoyancy force, the fluid force 1. Buoyancy force 2, same thing, except it's with the amount of volume that fluid 2 is displaced, and the density of fluid 2. Okay, so that's buoyancy force number 2. The weight is similar. You do the mass times the acceleration still, so you have the density of the block itself, not the fluids, the block, and times the volume of the block would give us the mass of the block times the acceleration due to gravity. So the volume of the block is L, which is H1 plus H2 times the cross-sectional area. Okay? Now we're going to plug each one of these forces into our force balance over here. Plug each one of these, and we see right away that all the A's and the G's cancel out. So all these A's and G's can cancel out with the A's and G's on both sides of the equation. And we're just left with the densities and the heights. We see here the densities and the heights, and now we can put everything so that we're defining the density of the block. Density of the block equals rho 1 times h1 plus rho 2 times h2 divided by L, which is h1 plus h2. Great, so that is the density of the block in terms of the force balance based off of the buoyancy forces. Okay. Now part B, it says force balances on the block can be calculated in 2 ways. One, in terms of the weight of the block and the hydrostatic forces on the upper and lower block surfaces. And 2, in terms of the weight of the block and the buoyant force on the block as expressed by Archimedes' principle. Prove that these 2 approaches are equivalent. Okay, so we already did part 2, that's part A, where we looked at the force balance due to the buoyancy forces. Okay, so part 1, the reference plane I'm going to say is the top. The reference plane is the top right here of surface fluid number 1. Okay. So the thing that it's saying that you can calculate the hydrostatic forces only on the top and the bottom of the block, well, that's because all the hydrostatic forces on the sides of the block just cancel out. You don't set a block normally under normal circumstances. You set an inert block in a interface of 2 liquids, and the block doesn't start moving from side to side, right? It only moves up and down, sinks up and down. All right, that's because the forces on the sides of the block, they're all equally pushing on the block from all directions, and so it doesn't move side to side. Okay, so all those forces cancel out, and we're just left with the pressures on top and bottom of the block. So on the top surface, we have what's the pressure of the liquid at the top surface of the block? Well, it's the pressure at the top surface times the cross-sectional area, because force is pressure per area. Okay, so we have a pressure term here, and we're multiplying it by the cross-sectional area. So we have to find out, well, let's finish the force balance. Then we also have a pressure pushing on the bottom of the block, and it's the pressure right at the bottom of the block right here. And that is pressure 2, and it's multiplied by a cross-sectional area of the block A. Then we have the same weight that we did before. Okay, so let's define what the pressure is at the top of the block here, at P1. P1, well, we have our P naught term, which is our reference pressure. We don't know what the pressure is at the reference plane, which was at the top of the fluid. Fluid number 1. It could be atmospheric pressure, could be whatever. We don't know what it is. We'll just call it P naught. Okay. And then we also have all of the hydrostatic force pushing down on the block. So So we've got the density of fluid number 1 and then height H0 above the block, and that's the pressure at the interface there. Or not at the interface, that's the pressure at the top of the block. Okay, pressure number 2. Okay, we're pushing up on the bottom of the block. The pressure pushing up at the bottom is the P naught pushing down plus the fluid H2 times the density 2 of fluid number 2, plus on top of that we have H1 plus the density of fluid number 1, and then on top of that we have the same stuff on top of that we had before, which is H naught times the density of fluid number 1. So all of those hydrostatic forces in this region, until we get to the interface, and then in this region, all those add up to give us what the pressure is at P2. Okay, so that's P2 and P1. Then we have the same thing where we have all of these forces should sum to 0 because the block is not moving, it's stationary. And then we have P1 is negative. You can see it's pushing down on the block from the top. P2 is positive because it's pushing up on the block. And then the weight force is also negative, pulling the block down. Okay? And you have to make sure you multiply by the cross-sectional areas because forces are pressure per area. So you have to multiply it by the area that the pressure is working on in order to calculate the full force. Okay? So I'm going to pull the area out over here, and then I'm going to combine all these terms that we already solved for. And you'll notice right away that P naught cancels out with that P naught, and this rho g H naught cancels out with this rho g H naught. And we're just left with these two terms times the cross-sectional area. And we can substitute in the same weight that we calculated before, which was the density of the block times the length of the block times the cross-sectional area of the block times gravity. Well, now we see that we can factor out the area and the gravity of each of these terms. Cancels on both sides of the equation. And we're just left with rho H2 and rho 1 H1 times the density of block times L. And this is what we got before for the same part A in the same problem. And we can see now that the two methods are equivalent. Okay, so that is it for problem number 3.34. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.